Welcome everyone. In this video I'm going to guide you through the source code which allows you to connect your ADS1256 to an Arduino or STM32 and ultimately to your computer. So I have several videos from the past where I showed this circuit, but I was just showing the parts of the code and not the whole code together, and I was explaining all the different parts. And the goal of this video is to summarize everything and publish a whole and working source code. So I guess there will be a lot of people who will not watch this video and just copy paste the code, which I can understand. But if you do that, I ask you now to please subscribe my channel, and also if you found my explanation or the source code useful for your project, you can also donate me. You can find the donate button on my YouTube channel or on my website. So if you feel that I deserve the donation or the support, then I really appreciate it. So now let's get back to the code. So what I will show you here is an Arduino code, but it works with STM32 as well. I'm using the blue pill at this moment. So I'm using this STM32 Arduino framework, and that allows me to upload compile and upload the Arduino code to an STM32, and you don't need too much modifications, but I will show you everything, and I will also show you the alternatives if you want to use it with an Arduino. So let's start from the very beginning of the code. So the ADS1256 is a 8-channel 24-bit AD converter, and it's very powerful, mainly because of its resolution, but it is also relatively quick. So you can achieve 30 kilosamples per second. So for most of the hobby projects, it is quite decent performance. And either you use single-ended inputs, then you have 8 independent channels, or you can use the differential inputs, and in that case you only have 4 channels, but these are usually enough for most of the things. And since this AD converter has such a high resolution, you can use it to read load cells, strain gauges, or other things which require high sensitivity. So what we use here is, as I said, an STM32 blue pill, and the ADS1256 communicates with the microcontroller via SPI. So first of all, in the code you will find the SPI pins for the STM32, and these are the PA7, PA6, 5 and 4, and you can see the description for them. And in the square brackets you can see the pins for the same functions for Arduino. So on Arduino Uno or Nano, you have to find these pins and connect the in, the out, SCRK and CS pins to the corresponding pins shown here. But then there are other pins like the reset, data ready, and the power down pins, and those also have to be connected. So you also have to find your pins, but for these pins you can assign any kind of pins. You are not restricted to a certain standard or protocol, so you can find your own pins. And you have to make sure that you know which board you are using, because these pins, especially this pin here, can be different in or on a different AD converter. So you should check your AD converter, and you should also check my video in the corner, because I made a comparison between several different AD converters, ADS1256 boards, and I showed you that sometimes you have different pins apart from the standard SPI pins and the data ready pin. So you have to check that yourself. So I really recommend you to check that video. And then here we just have some comments about the clock on the board of the ADS1256. So I just need this set of numbers for further calculations, but I will show you everything. And then this is my default value for the registers. So we have registers and we have to write or read them in order to obtain data or manipulate something on the AD converter. So this is what we do here. And there is a nice register map in the datasheet of the ADS1256, so I really recommend you to check it. I put the link in the description for the original datasheet, so you can download it and enjoy it. So we have the 0 register, which is the status register, and then I wrote it like this. The multiplexer is used to choose the inputs, so I'm just using differential input. The AD-con register is set to 0, so the PGA value is 1, so we are not using the amplifier. It means that. The data rate register is set to 99, which is 50 samples per second, and GPIO register is set to 225, so everything is the default. And as I said, we connect via SPI, so here we have to include the SPI library. So we arrive to the setup. That's very simple. We start the serial and wait, and I have to tell you that the baud rate has to be high, because if you are using high sampling rates, then you want to push the data to the USB quickly. So use as high as possible or feasible, and then we just print some random message, and we run a function which is just a bunch of code, like starting up different functions on the AD converter, defining a few pins on the microcontroller, and so on. I will show you this function, of course. And we wait another 1 second, and we just confirm that the initialization is finished. And then when we set up our system with the microcontroller, then we reset the AD converter. So we set all the registers back to their default values, and then we write our own. So this function, basically a template, we have to write it ourselves, of course, but we can write it as we want, for example with our favorite settings. And whenever you start the Arduino or the STM32, these values which are defined in this function will be applied. And then print instructions function is just printing the instructions as it says, because how we control the ADS1256 is the following. So we usually send a letter, for example A or D or S, and that will do something with the AD converter, and then the microcontroller will send back something via the USB connection. So this is just telling us what kind of instructions we can use with this source code. So now we look at the variables. Vref, this will be used for calculating the output voltage. So we know that the reference voltage for this particular AD converter is 2.5 volts. Voltage is used when we just convert the values from bits to voltage. So this will be printed. This is the value stored for the chip select pin, whether it is 0, whether it is 1. So we know if we wrote it and it is set to high or it is set to low. Pins. So as I said, we have the standard SPI pins that cannot really be modified. And then apart from those pins, we have some other pins which we have to take care of. Well, this is in fact part of the SPI pin still. So this is the chip select or slave select pin. It depends on how people define this, but either you see CS or SS. So that is always there. And then we have the data ready pin, and then we have a reset pin and a power down pin. But this can be sometimes the same as the reset or sync. Again, check my video where I talk about this thing, because this is very important to take care of, because these pins has to be high if you don't write them. Otherwise the AD converter will not behave as you would expect. And you can see that here they are defined for the STM32, and if you are using an Arduino, then you have to define the pins in a different way. So probably it will be just pin number 4, pin number 2, pin number 3, or wherever you put these pins. And then I take care of the registers. So we use a variable for the address, we use a variable when we are reading something from the register, and when we are writing something on the register, and the register data is when we are fetching data from the registers, and this is when we are actually measuring with the AD converter. The direct command is just a character which is received through the serial connection. Conversion results is basically a set of strings put together. So we keep adding text to the string, and when we reach the certain threshold, we send it out to the serial port and we receive it on the computer. And the print message, that's again, it belongs to the print instructions function. So I just join all these small messages, you will see it how, which contain the different commands for the AD converter, and they are printed as just one single string. So we start to approach the more exciting part, which is the main loop. And in the main loop now we have a bit more complicated thing, but as you can see, I have commands in each line, and also when there is a relevant YouTube video that I already have, there will be a YouTube link. So if you get stuck with one of these, which should not be the case because this code is working as it is, then first you should check the relevant video, because then you will understand everything, and also you should check the datasheet. But what happens here is that we read our command character from the serial port, and then we have a switch case statement with a lot of cases, and then we check what we have. So let's say we received the small r, so then we read from a register, and what we do here is that we ask the user what they want, and then you can see that whenever I print something which is a text, so for example here down, and also for example here, there's a small star symbol there. And why I do that is because I'm using another software to actually visualize the data which I receive from the AD converter, and I want that software to neglect the non-numerical data, so basically everything which I don't measure. So in front of every text message like this, I have a star. So then that will be neglected by the plotting software. I will show you. So we ask the user what they want, and then we parse their answer basically, and which should be a number. So then we wait and we print the message. So it says basically that the value of the register number something, so the register that we picked, is this value. And that is printed out here. And then we just reset the value of this variable and wait for the next command. And I put an example here, as you can see. So if you send R1 to the Arduino or microcontroller, then it will return the value of the R1 register, which is the max register. And yeah, you have to notice that the registers start at 0. So you have a 0th register and the first, second, and so on. So now we go to a more complicated thing. So the small w is used to write the register. So first, you have to check, or you have to get the value for the register number. So which register you want to write. So we tell that to the microcontroller. And then we also ask the user which value we want to write on the register. And again, look up the datasheet and you will see which value corresponds to, for example, selecting the certain input pins, or selecting a certain AD conversion speed or sampling speed, and so on and so on. So we ask the value, and we also store the value in another variable that you can see it here, and we write it. And as you can see, there is a function for the write register which accepts two arguments here, the address and the value of the register. So we will look at this function later as well. So when we wrote that, then we say that the value of the register is this. So we basically read back the address that we gave here and print it here. That's all. Then we have this small t. This was just for me to use if the microcontroller answers, so I just wrote a random message here, and that's all. If I send a capital O, then we use this read single function, which just returns one single number. So you press O and press enter, and you will get here you will get two numbers, because one will be the raw data and the other is the raw data converted into voltage. If you send capital R, then you reset the ADS1256. You just reset it, so everything goes back to the default value, but you will not write your own values. There will be a different case for that. The case S is the sDataC command that basically stops all kind of data acquisition. So you just send this directly to the AD converter and it stops doing the measurement. We have this capital C that's used to cycle through the 8 single-ended inputs and measure the data or measure the values. The capital D is used to cycle through the 4 different differential inputs and then retrieve the data. The H is doing the same than the cycle differential function, but it's a sort of a high-speed function, because I create a small kind of buffer. I believe that I'm not doing the best practice here from programming perspective, but it seems to work. So I'm just collecting the acquired data in a sort of a buffer, and then I send that after a certain amount of data is collected. And by that, I can utilize the USB communication better. But yeah, this is not a high-level programming, so it might be wrong and it can be improved. But for me, it's fine. Then we have the small d here, and that is to send a direct command to the ADS1256. There is a table in the datasheet, you can see, table number 24. You can look it up, and you can see that some of these commands, like syncing, waking up, reset, they have their own standalone codes. So that's what we can send here, and then it makes everything more simple. We have a capital A that is just selecting one single channel and capturing the data of that single channel continuously. And before starting this, you have to manually select the channel. So you select your channel by writing a register manually through this set of codes, and then you have to send this command. And when you send this command, the ADS1256 will get back to you with all the data captured from one single input. And then this is a capital U. This is the default registers. So as I said, there is a point where we reset the ADS1256, but we set everything back to the default value. And after applying this or running this function, we can then use our own defined values for the registers and write them. So this is just some sort of simplification. So then let's jump into those functions which are defined in each cases. And the first is the read register. And again, there is a relevant video. If you want to look it up, you just check this YouTube link, but it's also in the corner of the video up on the right side. So we wait for the data ready pin to change the state, and then we start the SPI transaction. And according to the datasheet, we have to set the chip select pin to low, and then we send the following command to reach a certain register, and in exchange for that we can read out the register value by sending another dummy data to the or through the SPI. So then the value which we need will be shifted out from the AD converter, and then we store that in a variable. And after that we have to set the chip select pin to high and close down the transaction, and then we get back the register value. So this is like we want to reach the register number 1, so we have this operator here, the OR operator. So we OR together these two numbers and send it to the AD converter, and then that's all. So at the end, this function returns the register value. Then we can also write the registers, and there is another relevant video, which is basically the same video, because there is a video where I explain how to read and write the registers. So look it up if you are curious about the details. But basically we have the same strategy. We wait for the data ready pin, then we can start the transaction. So we start first with the chip select pin by setting it to low, and then we have to wait, and there is a timing diagram in the datasheet, and we have to delay with the T6 time, which depends on the clock source and so on, but that happens to be around 5 microseconds, or at least it looks to be enough. So then we first select the register which we want to write, and after that we send the value which we want to write on the register, and after that we just close down the communication by setting the clock select pin to high, and then close the SPI transaction. So here we have the reset function. As you can see, we don't have to wait for the data ready to change its state, so we straight away start with the SPI transaction, but still we have to put the CS pin into low state. We wait 10 microseconds. We have a direct command to reset the AD converter. We have to wait, and then we issue an sDataC. This is again in the datasheet, you can find it. So this has to be done in order to do the reset. So we wait again, and then we go high with the chip select pin and the transaction, and there is just a confirmation message. Then we have this initialize ADS1256 function. This is in the setup loop or setup part of the Arduino code. So as I said, we have to define a few pins, and here where we meet the chip select pin, so we set it up as an output, and by default we put it to low. We also have an SPI communication, and we have to start it. If you are using a dedicated ADS1256 STM32 development board, I also have a video about it. You can also see it up in the right corner. You have to choose another SPI channel for that, so be aware of that. But here with STM32 with a separate AD converter or Arduino, then you just start this. And we also store the value of the chip select pin in another variable. And then we go for another set of pins. One pin is the data ready pin, that's an input. And then we have the reset pin, which is an output. And we set the reset to low by default. And then we wait a little bit, and then we set it to high and leave it like that. and this is done. So this is basically the initialization sequence. I just did not want to squeeze all of these things in the setup, so I thought write another function for it and just put the function in the setup. It works. So now we arrived to the first most simple part of the reading, when we read a single conversion. So that means that you send a command to the microcontroller, which will send a command to the AD converter, and the AD converter will return with one single measurement. There is a relevant video for that, so please check it, especially because this part is explained there, which is very important if you want to understand the very basics of how to shift out, for example, to 24 bits of data. So then again, we wait for the data ready pin, and then we can start our transaction, SPI transaction. Then again, we have to go low with the CS pin, and we have to issue the rdata command. So we have a direct code for that, which is either this long binary code, or you just send the number 1, because as you can see, this is the 1. So we transfer that, we wait 10 microseconds here. This seems to work. However, if you calculate it, 6.5 microseconds should be enough, but for me 10 looks safer. So then we have this more, let's say, difficult data. I'm not really going into the details because I have another video where I explain this bit by bit, but basically what you do is that first the most significant bit comes in, but that is, let's say, on the very right side of the 24 digits. So then you have to shift it to make space for the next 8 bits. So now this part is in the middle of the 24 numbers, so in the middle 8 numbers, and then we made a new spot available for the next part, for the mid byte. So then that arrives to the right 8 bits, and then these guys now together shifted to left. So we have occupied, let's say, if we start from the left, then we occupied 16 bits, and then we have 8 bits available for the last part. So that's the least significant bit. So that's what happens here. But I made a very detailed demonstration of this in my video, in my other video, so please check that. So once this is finished, we just simply print it, and I also have a function where we convert this into voltage. So we also print that, and then we close down the data acquisition by pulling the chip select pin back to high and ending the SPI transaction. Then we can do the same thing but continuously. So we pick one channel and we continuously read that one channel. Again, there is the relevant video link here, and then we just first start zeroing out the register data, because, for example, if you have some data in it and you start shifting on that data, you might end up with some funny numbers. So it's just better to set it back to 0. So here, at least in this part, we don't wait for the data ready, but we start setting up the things. So SPI and then chip select pin. And then we have the direct command rdata_c. So we send that and wait for 5 microseconds. And then we basically enter in an infinite loop, which is a while loop here. So as long as this condition is not met, then this code runs over and over. So here now we wait for the data ready, we wait again 5 microseconds, and we start shifting out our data into the register data variable. And then we print that on the serial terminal. And temporarily you can put this here by uncommenting this part, and then you can get the voltage as well. But I did not want to have it, but I keep it in the code so you can use it. And after each conversion and printing, of course, you have to reset the register data. So this is done, and then when you send a small s to the serial terminal, then this while will exit, and then chip select goes back to high, and the SPI transaction is done, ended. Then we want to read more pins. So we have to cycle through the single-ended pins. There is a relevant video again, so please check that. So we have cycles. I start from 1. We have the register data, and then we start the SPI, and then we have another while here. And we go from 1 to 9. Yes, we can go from 0 to 8 as well, but for me it's just more easy to think about like this. We start from channel 1 and we end at channel 8. So I put some information here and I will not read it, you can read it, but the basic principle what I try to say here is that since we already defined the first input channel as the A0 pin plus the common pin, then we start with the channel 2 here. So as you can see, this is not A in 0 plus A in com, but A in 1, because the first channel is already in the register, and then when we write the next register, that has to be the second one that we want to read. And then here there is also a drawing that this is already in, but then within this switch case part, we start from here and basically end here. And what the code sees in this function is basically this part, but what we will receive is this part. I hope it makes sense. So we already started our loop, and we already started going in the for loop as well. So we wait for the first data ready feedback, let's say, and we switch to the next channel. So then we switched to the next channel, and then we sync, and then we have to wait, and then we have to wake the AD converter up and send an rdata command. And after that we wait again, and then the data will be available, so we have to shift it out. And then what we do is basically start to put together the string. So we have the conversion results plus the register data, and this is a string, and this is an empty string in the beginning, so basically we just have the register data in the first iteration of the loop. So then after doing this, we also add the tab to separate the subsequent data. Then register data goes back, chip select goes back, and here you can see how we expect our data to look like. So basically what we did, register data, this part, and then we did a tab, this part. And then the next came in, the next iteration of the for loop. So we were able to write this part in it, and then in this part, in this line, we put a tab here. And then this goes on and on until we have all the 8 channels. So then we have the 8 channels. Then we step out from this for loop, and we print the conversion results, which is here. So this line. And then we reset this so we can start to fill it up in the next iteration of the while loop. So this is basically it. So in the next iteration of the while loop, everything starts over. So we first go into the for loop, start with this pin, print it out, go to the next pin, print it out, go to the third pin, and so on until we reach this. So we can do the same practice with the differential inputs, and that is very, very similar to this. We only do one thing differently, and that is basically we define the input register in a different way. So previously we did like this, so we picked one pin and always pick the common pin as the negative pin. But what we will do here is that we will pick, for example here, one pin and another pin as the positive. And here, so let's start. We have a relevant video again. So we have a cycle, but this will only go from 1 to 4. So first, second, third, and fourth differential input. We zero this out. We start the SPI. We start pull down the chip select to low, and here I do this thing, which is, as you can see, we write the register number 1, which is the max register, and I always define the first pin that we want to read as the A in 0 and A in 1. So now the AD converter will know that this will be the first pin that we measure. And then chip select pin goes high, and we end the transaction. But this transaction here was just to always start from this A in 0, A in 1 pins. And then we enter our while, and of course we have a for cycle again. So here we get stuck until we get the data ready pin change its state. And then we start with the switch case here. So again, we have a input pin combination already stored in the AD converter, but we start to define the next one. So the principle is the same as it was up here, but instead of 8 channels, it's only with 4 channels. So we start and we say which will be the next input pin, and you can see the pairs here, 2, 3, 4, 5, 6, 7, and then we go back to 0, 1. And then we have to sync, wait, and then we have to wake up, and then we issue an R data, we wait again, and we start to shift out the data. And then we put together the data in the same fashion, but instead of getting 8 columns in a line, we just get 4 columns in a line. And after we finished the for loop, so we went through all the 4 pin pairs, so inputs, then we just print the conversion results. So this set of data will appear on the serial terminal. And if we abort the while loop by sending a character S, then we just exit like this. And that's all, because this will always go back to high, so we don't care about that, and we just have to exit the SPI communication. So then we have this cycle differential HS function, which should be the high-speed function, and this function is really identical to the previous one, except basically this part, so how we construct the output. So now we have 2 embedded for loops, everything else is identical. So we have this let's say package for loop. What this will do is that it runs the next for loop for 10 times, which looks maybe a bit dumb, but let me explain it to you. So we just run the same thing, but then here. So until this point, the code looks the same, and then here we check the number of cycles done. And as long as it is smaller than 4, we just keep adding tabs in between the numbers. But then when we reach the last iteration of the cycles, so this actually is not valid anymore, and we enter the else part, we don't put the tab at the end. So then what happens is that, of course, we just reset these things, but we come out from the innermost for loop, and we meet this part, the conversion results. And here we just add a line break after having 1 line of data. And then we go back and we start our cycles again. And we do this again, and we do this 10 times. So then we print a line within this part, we exit, So we add the line break and then we print. And as you can see, this is not being printed on the serial terminal. So after finishing the 10 loops here, as you can see, we leave this loop and then we print the whole thing. So basically 10 lines at a time, we print that on the serial port. And then we reset this now quite big string, and we just abandon everything if we just stop this part. So this was quite easy. And yeah, it seems to be faster. But if you have a better method to send data to the computer, please let me know in the comments, because I'm really curious about how to improve the performance, because I can see that this is one of the bottlenecks of the code. So then another function is that we can send direct commands, which I really like. Is that you just punch in a bunch of numbers and you can trigger different functions of the AD converter. So that makes everything very easy. Because, for example, you can have a predefined list with all of these commands, and then whenever you want to send some command all of a sudden, you can just trigger something which sends a certain command, like resetting the AD converter or doing a self-calibration or something like that. So that happens here. And it's the same pattern. Start the SPI, pull the CS pin to low, wait the usual 5 microseconds, transfer the direct command. So you can see that here we just avoid using the write register. We just straight away sending an 8-bit number. In fact, there is a direct command for writing the register as well and reading the register as well. But here we can modify or manipulate other things without going through the write register part. And then we wait again, chip select pin goes high, and we end the transaction. Then we have these user default registers. So this is what I was talking about, which should be done after resetting your AD converter. So when you reset the AD converter, you get the factory defaults on it and not your own defaults. And what this function does is basically that you define your own defaults and you send them to the AD converter. So these are my own defaults here. So status register is 54, and the multiplexer is 1, the AD converter is 0, and the data rate is 99, which is 50 samples per second. We update all of them. So as you can see here, we just wait a little bit before doing anything, and then we just straight away write the registers. So of course these are functions with 2 arguments. So within this function you will do the SPI begin transaction and waiting for the chip select pin and so on and so on. But here we just say that okay, write the 0 register and write this number on it. And then we wait a bit, and then we write the next register, and then wait, next register, and then wait, next register, and we perform a self-calibration. And that's all. We print a confirmation message and done. So when this is done, either you manually check if the values are really those values that you want, or you just trust the device. And then this is the print instructions. As I said, I just want to print the instructions. So if you forgot which character to use, then you can easily look it up. So what I did, I just took my own notes and check what is what. So this character will tell you how to read the register and so on. And as you can see, we have examples everywhere. So you will see what happens when you send, for example, this kind of code. So you can test it yourself. So first we just create this huge string. Maybe this is not the most efficient way, but here we don't care about speed or memory or anything, so it can be what it is. And then we print it on the terminal, and then we just empty this variable, and that's all. And then the last function is this convert to voltage function, which you could see probably up here. So for example, it was this was the continuous conversion, or this. So that function in the bottom of this code basically just takes care of the raw data and converts it into a voltage value. So here we just check the 24th digit in our 24-bit number, and if the first character is 1, that means that the number is negative. So then we have to sort of mirror the number. So this is what happens there. Mirror it around 0. So we make it into a sensible negative number. And then we convert the number into voltage. And how it is done? It is done with this formula. You can also look it up in the datasheet. There are different definitions for the output voltage. But yeah, what we do is 2 times the reference voltage divided by 2 to the 23rd power, and we subtract 1 from this big number, and then we multiply this whole thing with our raw data, and that's all. And then we print the voltage, which we just calculated here, on the serial terminal with 8 decimal precision, so a lot of decimals, because we can measure microvolts even. So if we don't format it, then at least we can see it, that the microvolt region is really measured. And then finally we just set the voltage back to 0, so nothing can get mixed up or something, and we can wait for the next data to come. So then at the end of the file I left some comments and some useful data or useful thoughts, ideas in it, so you can check it and use it as well. So then, to finalize this very long video, I want to tease something else that can be useful or can be fun. So I have a client software for the ADS1256, or for basically any kind of data acquisition in general. So I want to show you that it works with this AD converter, and it uses all these functionalities that we programmed. And obviously it's a nice proof that my program works. But first I just start the serial terminal, and yeah, we can just very quickly go through this, so we can just see the raw data that goes through the things. So we have the serial monitor here, and the STM32 is already connected, and as you can see, when you open the terminal and you have an STM32, it doesn't reset it as compared to the Arduino. So whenever you open a new terminal, the Arduino will be reset, but not the STM32. So that's why I made this T function, that we can see that it is connected. So now what I have a multimeter in front of me, so I turn it on, and yeah, I just don't want to discuss anything about this circuit. I will just put a picture somewhere on the video, but yeah, I just basically have a potentiometer connected to a power source and then to the AD converter, just to have a variable voltage, so I can show you that we can measure voltage. And now at this moment I'm measuring 1.096 volts, and I take a picture of it and I will put this on the video. So if you remember, then we have this O command which returns a single conversion value. So I send it, and there we go. So once again, so this is the raw data, the bits, and this is the output voltage. And as you can see, this is pretty much 1.096. I changed the potentiometer a bit. What should be the value? 1.529. So let's see what happens. Yeah, it's pretty much same value. So this works. So now the next command is, for example, let's just read the first register, and here, so in the beginning of the code, this should give us 1 back. and it is 1. If I read the 0 register, it gives 54. Let's read the third one. So you can see that we pretty much have these values here. So now let's send the A command, which is the continuous acquisition, and that just prints the raw data, so you won't see any nice numbers, but yeah, just see it. So you see, and now I start to turn the potentiometer just to show you that the numbers are in fact change. Yeah, so this is also working. So we send the letter S, that should stop everything. Done. So now let's go for 4 channels, and for that we will use the differential mode. But we have to keep in mind that there is nothing connected to the rest of the channels, so this won't show any exciting results. But you can see that now the numbers are coming, and yeah, so something is there. So we get just some weird numbers, and basically pretty much that is what we should expect. So it's some numbers. If I stop it, then it stops. We can start the reset, so that is basically this. So now the AD converter is reset. So yeah, you can see that now the numbers are coming in a very quick sequence if I start a single channel acquisition, because if you reset it to the factory values, then you will pretty much get, I think, the highest acquisition speed. So this is like 30 kilohertz. If I go to the 4 channel, you can see that this is very fast. And now I try to turn the potentiometer and change the value, and the first channel is indeed now it's changing. And yeah, this was previously the number when I just left it at 0. So yeah, now I turn it and it works. So yeah, this works. We can set back our favorite settings, which is updated. So now if I press the A, which is the continuous acquisition, the speed should be more slower, and you can see that it's reasonably slower. So this was all for the terminal, and let's check something more spectacular. So this is my nice little toy, which is the 8-channel data logger, and it's basically universal. And what I mean by universal is that as long as you send your data in this kind of format, you can even send the built-in AD converters values from the Arduino. So I wrote this software in a way that, yes, it is mainly controlling the ADS1256, but it's not a problem if you don't have it, because you can also just use it to capture the data from the AD converter of your Arduino or STM32 or whatever device that can connect to the COM port, like here, and can send the numbers in such a format. So it's basically number and then some separating character, and then number, separating character, and then line break at the end. And this set of data will belong to one timestamp basically. So what we have here is we had to connect to the COM port, and now I have to set it up in a proper way. So I made another form to have control over the sampling rate. Let's put it to 100 SPS. The chart refresh rate, this is in hertz or FPS, so how quickly you refresh the data, because you might collect 15,000 data points, but you don't want to show them because first of all it's a lot of resources, but also you cannot comprehend it with your eyes, so you cannot resolve it. So why show, for example, 15,000 data if you cannot do anything with it? So we don't refresh the data that often, we just refresh maximum with 60 Hertz. You see it continues enough to read the most significant values. And then PGA, that remains 5 watt. This is the measurement length, what it means that if I check this, then 600 minutes will be the measurement time, which is 10 hours. So after 10 hours, this software will stop and stop the measurement and save the data. And the time window is basically that what we have here is the data starts from the left side, of course, that's because here we have the origin, and then we get point 1, point 2, point 3, point n. And basically, since we print on the screen every 1 second, then after printing for 10 seconds, we start to move out the data on the left side and move in the data from the right side. So the chart will look something like an oscilloscope or something like that. You will see it. So this is what it does. So we just keep 10 seconds of data at a time on the chart. And then this is for, basically for other commands, that if you write another software or you control another AD converter, you can still have the data formatted in this, or for example, you can separate everything with a comma and so on and so on, and you can tell it to the software. And so here I just use the most popular separating or delimiter characters, and I will use the tab, and here we just have some predefined file name. You can save all the data in a file name, in a file. So we set the parameters, and here I have some small debugging window, so I can see what happened. So we set the samples per second, the reference, and so on and so on. So this is just important for me. So here I select the differential input, and I select the first channel, and you could see that when I selected the differential input, then I got half of the channels disappeared. So when I do this, then the rest comes back, and then these go away. So everything is set up, so I just start. So now you can see that it goes out from the screen, for example, but you can see that the Y scale is always auto-scaling itself. So you can see that this is 2.42 and this is 2.424. So it's a very small voltage range. And I start to move the potentiometer, then it's rescaled again. And you can see that it's quite nicely following. And now I move the potentiometer up and down. So you can see that this is continuous. And as the things are moving out, and now I set it to 10 seconds. So after 10 seconds, this part will be on this side and it will move out. But what you see here is quite continuous, and we always see the most recent data. But of course you can squeeze on a whole days of measurement here, but then that might not look very nice. So you have to experiment with this. But I still have to adjust this software because sometimes it doesn't behave as I want, so I have to debug it a little bit more. But it works most of the time. I can also add more charts, whatever. But they are not connected to anything, so I cannot really do anything with them. Maybe I can connect one more. I try to connect it at least without shorting out things. There we go. So now they are connected to the same, and you can see that the red and the green following each other very nicely. And that also proves that the cycling is a very quick process. So when you change from channel 1 to channel 2 inside the AD converter, that happens very fast. And now one cable got loose. So you can see, I don't know, that's probably the capacitor discharging. Let's put it back. So this was quite a long video, but I really wanted to explain everything, so there won't be any confusions or just a small amount of confusions. So I hope that you find this video useful when you finish it, and I hope that you learned a lot from this. Also, don't forget to check the description. I put the related playlist there, and I also put my website link as well. So you can check the source code, you can download the source code, and so on. So please don't forget to subscribe to my channel, that helps me a lot. If you have some other questions regarding this circuit, yeah, just leave a comment and I will try to answer it. But please really watch the video, because usually I can see that most of the questions which I get are answered in the videos, but people are not really watching them. So then, yeah, I cannot be blamed. Yeah, so this was all regarding the video. If you want, you can also donate me, and that will help me to create more content and use more advanced circuits, for example. So I can buy them and write codes them, which I later be able to publish and so on. So this was all, and see you in the next video.